Welcome to our comprehensive course on machine learning systems. In this video, we'll explore the crucial concept of designing ML systems for scalability. Scalability is what allows your powerful ML models to handle real-world demands, from massive data streams to millions of user requests. We will examine the key challenges, infrastructure needs, and optimization techniques required to build truly production-ready applications. Let's get started with understanding this vital requirement. Welcome. Today we are discussing designing machine learning systems for scalability. Scalability is simply the system's ability to cope with growing demands without failing or slowing down. When building an ML system, scalability is one of four core requirements, along with reliability, maintainability, and adaptability. In simple terms, a scalable ML system must efficiently handle more data, more users, and more tasks. This is crucial because ML in production must support fast inference and low latency. For instance, a system serving millions of predictions hourly, like Google Search, needs massive scalability to handle the computational load. ML systems are complex structures made of algorithms, data stacks, business rules, and the infrastructure underneath, all needing to scale as one unit. If one part bottlenecks, the whole system slows down. We must consider the entire system holistically when making design decisions for scaling. Understanding this comprehensive view sets the stage for success in applied ML. This diagram illustrates the four primary requirements for robust ML system design: reliability, maintainability, adaptability, and our focus, scalability. Scalability is the key to handling massive growth in production environments. Specifically, a system that scales can manage significantly higher volumes of data, support many more users, and cope with rapidly increasing computational demands. When we talk about designing for scalability, we are planning for growth across all these dimensions, right from the beginning, ensuring the system can handle future load effectively. This preparation distinguishes successful production ML systems from academic prototypes, which often deal with static, clean data. Designing for scalability minimizes bottlenecks in computation, data processing, and inference speed, allowing the system to maintain low latency even under heavy load. We learned that scalability is fundamental for production ML, ensuring the system handles increased load across data, users, and compute resources. The important point is that unlike research, production demands low latency and stability under massive, continuous operation. Our first scaling challenge focuses on data. Modern machine learning models, especially large language models, thrive on massive amounts of data, sometimes involving hundreds of billions of tokens. Working with this huge volume, which might even reach petabytes, is challenging for conventional processing methods. Furthermore, real-world production data is almost never clean or static. It's messy, noisy, unstructured, constantly shifting, and potentially biased. We also face the challenge of data velocity, meaning data streams into the system very quickly and must be handled in real time. Scaling involves setting up robust data systems that can effectively collect, move, store, and process this growing and complex stream of data. Poorly managed data can sink the entire ML operation. This emphasizes why data engineering fundamentals are critical for designing scalable ML systems. This diagram highlights that data scalability is driven by three factors: volume, velocity, and complexity. The volume of data is enormous, with many models relying on petabytes of information. As seen in the growth of language models, datasets are now in the hundreds of billions of tokens, making scale mandatory. Velocity refers to data arriving quickly, often needing real-time handling. Complexity includes the fact that real-world data is messy, noisy, and unstructured, unlike controlled research data. Crucially, the underlying statistical properties of this data, known as data distribution shifts, change constantly, which can cause model failure. To overcome these hurdles, robust infrastructure is required for efficient storage, retrieval, and processing, forming the base of a successful ML system. We learned that data scaling is challenged by huge volume, high speed, and inherent messiness. The important point is that production data is dynamic, requiring continuous management and robust data engineering to handle changes and maintain quality at scale. The second major scaling challenge is managing the sheer size and complexity of the models themselves. Modern ML models are huge, often having hundreds of millions or even billions of parameters. These massive models demand gigabytes of RAM just to load them into memory. Getting these models to production, especially on smaller computing platforms like mobile devices or IoT gadgets known as edge devices, is a significant engineering feat due to limited memory. Even once deployed, the model must run fast. Low inference latency is critical. If an auto-completion model takes too long to suggest the next word, it becomes useless to the user. Furthermore, increasing model complexity directly translates to increased computation time during training and inference, forcing us to use specialized techniques like distributed training to manage efficiency. We need innovative ways to make these large models run fast and efficiently on available hardware. This diagram shows how a large machine learning model creates scalability issues. These models often possess billions of parameters, and thus require vast resources, specifically gigabytes of RAM, to run effectively. This creates a resource constraint, especially when trying to deploy the model on resource-limited hardware, referred to as edge deployment. A critical demand for system scalability is achieving low inference latency, meaning fast predictions, which is vital for user experience. To overcome the difficulties presented by model size and complexity, specialized strategies are necessary. These mitigations include using model compression techniques, which we will discuss later, to make models smaller, and employing distributed training to manage the high computational cost of creation. We learned that large models demand low latency and efficient use of massive resources. The important point is that model size and complexity must be actively managed using techniques like distributed training and compression to ensure real-time usability. To achieve scalability, strong infrastructure is non-negotiable. This infrastructure includes intelligent resource management for storage and compute power. When dealing with large models and complex tasks, GPU instances are critical. GPUs excel because their parallel computing architecture allows them to handle far more floating-point operations per second than a standard CPU, accelerating training significantly. When a model or the training data is too massive to fit on a single machine, we must use distributed training. This process splits the workload across many computing instances. There are two primary types of distributed training: data parallelism and model parallelism. Data parallelism copies the entire model onto each worker machine and feeds each replica a different slice of the data. Model parallelism, however, splits the layers of the model itself across different workers. Both methods can be combined for maximum hardware utilization. This visual compares the two main strategies for distributed training, which is key for scaling computation. In data parallelism, the full dataset is split, and a complete copy of the model runs on each worker with its subset of data. The results, or gradients, are then combined to update the central model. In contrast, model parallelism is used when the model itself is too large for one machine. The model's layers are split across multiple workers, creating a sequential flow where the output of one worker feeds into the next. Both approaches rely on powerful GPU compute infrastructure to handle the parallel floating-point operations efficiently. Leveraging these strategies is how companies train massive models rapidly, making large-scale ML feasible. We learned that specialized hardware, GPUs, and distributed strategies, data and model parallelism, are vital for handling large-scale computation. The important point is that distributed training makes training models that exceed the capacity of a single machine possible. When scaling ML systems, we must decide how to process data to make predictions, typically choosing between batch or online modes. Batch prediction involves generating large sets of predictions periodically, such as generating customer reports overnight. This method is less sensitive to inference latency. In contrast, online prediction requires the model to respond almost instantly to an individual request, demanding extremely low latency. Online prediction often requires extracting streaming features from incoming data in near real time. For systems like fraud detection or highly responsive recommendation engines, online prediction is mandatory. Online prediction allows the system to be much more responsive to a user's changing preferences or new data, directly supporting the scalability requirement for adaptability. The scalability challenge here is building a reliable pipeline that can manage this high-velocity, real-time data flow. This diagram shows the fundamental difference between batch and online prediction services, a core design decision for scaling. Batch prediction uses stored historical data, processes it periodically, and saves the results. The demands on latency are lower. Online prediction, necessary for maximum responsiveness, starts with a user request and uses real-time transport to process streaming data. This data is immediately used for feature extraction and fed into the ML model to generate an immediate prediction. Online prediction services must be highly scalable to manage continuously incoming data velocity and maintain inference speeds within milliseconds. The ability to handle high throughput and low latency is what makes online prediction key for highly interactive, scalable applications. We learned the difference between batch and online prediction, emphasizing that online prediction is vital for high-speed, scalable systems, as it handles real-time data flow and must maintain extremely low latency. To truly scale a model for high throughput and low latency inference, especially in online systems, optimization is mandatory. We achieve this using compression techniques that reduce the model's size without sacrificing much accuracy. One powerful technique is quantization, which involves reducing the precision of the numerical values used to represent the model's weights, often going from 32-bit floating-point numbers down to 8-bit integers. This significantly shrinks the model file size and speeds up calculations. Another method is knowledge distillation, where a large, powerful teacher model is used to train a much smaller, faster student model. The student learns to replicate the teacher's prediction behavior, leading to a smaller model that is easier to deploy at scale. Lastly, pruning identifies and removes non-essential parameters from the network, making the model sparse and quicker to run. These methods are often combined to achieve the best scaling results. This visualization shows how model compression techniques contribute to scalability by optimizing large models for fast inference. The process starts with a complex, often large teacher model. Key techniques within the optimization step include knowledge distillation, which produces a smaller student model with comparable performance, and quantization, which reduces the numerical precision of weights to shrink the model file size dramatically. Additionally, pruning eliminates unnecessary weights to create a leaner, sparser model. All these methods lead to a smaller, scalable model, capable of fast inference and low latency, making it suitable for high-throughput production environments and constrained edge devices. These optimized models are essential for maintaining the performance expectations of a scalable ML system. We learned that model optimization via compression, quantization, distillation, pruning is essential for reducing model size and latency. The important point is that these techniques allow huge models to run fast enough for real-time applications and deploy successfully on smaller hardware. Scaling an ML system isn't just about the data and the model. It's also about scaling the human workflow. ML model development is fundamentally an iterative process, requiring constant repetition of steps like data preparation, training, evaluation, and deployment. To maintain and improve models continually, especially as the number of models grows, we must move away from manual, ad hoc processes towards automated retraining. ML workloads are inherently repetitive, such as running a training job every week. To manage this complexity and repetition, we use tools called orchestrators and schedulers. These tools, like Airflow or Argo, manage the entire workflow, which is typically defined as a directed acyclic graph, or DAGE. Automation through orchestration ensures that critical, repetitive steps, such as pulling fresh data, extracting features, training the challenger model, and deploying the new champion, are executed smoothly, reliably, and cost-effectively, reducing manual effort and enabling high-frequency updates necessary for adaptability. This diagram shows the continuous, iterative process of ML system operation, which must be fully automated to scale effectively. The workflow is a cycle, starting with a trigger for retraining. Steps include pulling fresh data, extracting features, model training, and rigorous evaluation and testing. Only if the new model, the challenger, passes all tests is it deployed as the new champion. If it fails, the system reverts or triggers an analysis. This loop closes with continuous monitoring, providing feedback for the next iteration. Tools known as orchestrators manage this sequence, ensuring dependencies are met and resources are used optimally. Scaling the system relies entirely on automating this cycle, moving away from manual maintenance towards high-frequency, reliable updates. We learned that scaling maintenance requires automating the iterative ML workflow using schedulers and orchestrators, DAGs. The important point is that automation via tools like Airflow or Argo is crucial for enabling continuous, high-frequency model updates necessary for system adaptability. We have completed our overview of designing ML systems for scalability. The core takeaway is the necessity of a holistic system approach. We cannot focus only on the ML algorithm. We must consider how data, features, infrastructure, deployment, and monitoring interact and scale together. Remember, building an ML system is an iterative process, a constant cycle of improvement, not a one-off task. A scalable and successful ML system must meet the 4 key requirements. Reliability. It works correctly even when things go wrong. Scalability. It handles growth in data and load. Maintainability. It's easy for different teams to work on. And adaptability. It handles changing environments and requirements. To start any new ML project, remember to begin with the simplest model as a baseline, focus heavily on data quality and feature engineering, and automate the iterative workflow. These steps ensure your system is robust and ready to handle scale. This C4 model provides a holistic view of a production ML system, emphasizing that true scalability requires all components to work in harmony. The system relies on a robust data stack for handling large volumes and high-velocity data, and powerful compute infrastructure supporting massive models through distributed training and orchestration. The ML model logic generates the predictions, which are served via deployment mechanisms, either batch or online, focusing intensely on low latency. Continuous monitoring ensures the system detects performance degradation or data drift, feeding back into the data stack for updates. The entire scalable system exists to serve the stakeholders and achieve defined business objectives. Failure to scale or maintain any one component will compromise the entire system, stressing the importance of this integrated design approach. We learned that scalability requires a holistic, iterative approach, encompassing all layers of the ML system. The important point is that the system must continuously adapt and maintain the core requirements: reliability, scalability, maintainability, and adaptability to ensure long-term production success.